I'm going to start this lightning talk with a little warning. I'm going to be doing some shader programming, and there will be some music. So if you have stuff regarding the loud sounds and flashing lights, this might be a good time to leave. I'm not trying not to overdo it, but who knows? I might program something wrong and that it flashes a lot more than I intended, and stuff happens. So, since the beginning of computers, human has wanted good graphics. There's been a quest. We had oscilloscopes where we made drawings. We then had the calculators where we tried to make nice diagrams. And then somebody got a hold of an Atari and played around with sprites. But the problem is, though, good graphics takes a lot of computing power. So after a while, we got dedicated hardware, GPUs that run and parallelize graphics programming and graphics rendering. And it's kind of funny that in this time when all the stuff we do end up on the same computer, there is still dedicated GPUs and like a small computer for just making graphics. That's how much we love to look at nice visualizations. So with dedicated hardware, we had the problem that we needed to program them in a special way. And after a while, OpenGL arrived. It was an API for writing software that was going to run on a GPU and writing software that was going to make a nice image. If we go forward a couple of years more, we ended up with WebGL. And it was a kind of a side project that ended up being a big project at Mozilla, where somebody tried to implement something like OpenGL, but something you could use in a browser, like a JavaScript. Still write some OpenGL stuff, compile it to like code that could be run on the GPU, send it over, and get the graphics back and all that good stuff. And it turned out all right, and we had it for a while, like 2011. It's not last year. And it runs in almost all browsers I know of. I can open a mobile phone and I can write shader code. And my smartphone will have a GPU, and that GPU will accelerate my nice graphics and display it in a nice and simple package. So that's what I'm going to talk a bit about today. My name is Teodor. I work as Computas, and I'm a software developer, mainly working on all the stuff that I find interesting, so yeah, not really specializing. But this thing was something that became kind of a love project for me, because it's something special when you have your code running and then the screen comes alive with colors and all that good stuff. So I'll not be able to cover the entirety of WebGL in a 50-minute lightning talk. So I'm going to focus on a very specific thing, and that is writing fragment shaders. So OpenGL contains a lot of stuff. You have stuff regarding 3D, like some 3D models you can load and that part, and then you can write the vertex shaders that works on those 3D geometry. But finally, you get to the fragment shader, or the pixel shader. And the fragment shader is responsible for taking the output of the rest of the pipeline and doing the final rendering of the image. Like you get some information, and then you have to return a color value for every pixel on the screen. And you don't get much information to work with, because since this stuff is going to be parallelized on the GPU, you can't know anything about the other pixels. What are my neighboring pixels doing? I don't know. I only have to work with the stuff I know about myself, my placement, and then some secret sauce that we'll get to later. But that's also a nice programming model, because it maps really well over to functional programming, where you have like map functions that you apply on a large list, in this case sort of like a 2D list of pixels, and then you get out a single value. So we're going to start with getting a color on the screen. And what we're currently looking at is a web page, and it's running a simple editor. And in that editor, we have GLSL. That is like a special purpose language for writing shaders that is defined by the WebGL specification. This stuff looks a lot like C, and I don't think that's unintentional. And it's really focused on performance, And not always so much on developer comfort. It's at least some things I find strange here. A nice thing yesterday when I was sort of finishing up my talks, I was playing around with this page, and Chrome always wanted to tell me that it could translate French. So that might say something about how Chrome thinks GSL is. And like C, we have a main function, and main function is sort of the thing that runs the entire shader. You need to have a main function, or OpenGL will complain a lot. And then you have GL frag color, and this is sort of your output from the entire shader. I would love to see, like, instead of a void, there was a return statement, but yeah, this is the way GLSL likes to do it. GL frag color is something you give 4 values. You're most concerned with red, green, and blue, because red, green, and blue we can make to make different colors. And then you have an alpha value, which sort of like how much color do you have in this specific pixel. At this point, I only have the possibility to return a color, and it has to be the same color for every pixel. Remember, this code will be run for every pixel on the screen. And since I don't know anything more, the only thing I can do is to make a solid color. So in this case, a nice shade of purple on my screen. I'm not really sure what we should call it up there. Maybe try to give it a little more red, maybe. Yeah, a little bit stronger, perhaps. Let's probably go with a green. So these colors are pretty much the same you expect from a web page, except they go from 0 to 1. So in web, we usually are used to working with values that go from 0 to 255, and somewhere around there. But the numbers from 0 to 1 is really easy to do math with, so that's why GLSL will make that conversion for us. Yeah, still quite white. Let's maybe go for a little blue. Yeah, well, it's not purple anymore. So turning the entire screen the same color isn't that much fun. So we would like to do something a bit more interesting in that. And to do that, we can have a look at the position that each pixel has. And the position we can get from a magic constant called GL frag color, frag chord. You can sort of see how GLSL likes to do stuff. There is magic constants going in, and there is other magic constants going out. GL frag chord is a vector of 4 values. So like we see in here, going out, we sort of send out 4 values as 1, and that 1 value is a vector type. And you can think of a vector type just like a very short array, and that array has a fixed length. And it's nice to work with vectors because we can do stuff with the entire vector. We can multiply them together. We can multiply them by constant, maybe. Like, let's say we wanted this to be 2 times more than what it is. Yeah, and then it gets whiter because the more color we have, the closer we get to white. Maybe we want it to get to be a bit darker. We can divide it by 2 instead, perhaps. And it turns a little bit darker. But why is this frag coordinate 4 values? I know every time I move my mouse around on the screen, I only get 2 values, like an X and Y value. Well, there is some more values in there, and they're usually used when you're making shaders that involve a larger rendering pipeline. So we're going to only focus on the first 2 values, the X and the Y value of the pixel. And another nice thing about vectors is that you can easily access parts of them. So like by convention, the first value in the array or the vector is called X, and the next one will be Y and Z and so on. So by doing this, I would only get the first value of the frag chord. And this, in case, would be a float. And we probably would call that float for the X position. But GLSL has something nice when you're accessing vectors. Oh, there went the sound. I think it's out of battery. But you might not have a problem with me speaking without the microphone. Is that okay? Yeah, then I just go on. So where were we? Yeah. I was going to make a vector only containing x and the y values. So like we want to throw away the two last values, we only want the x and the y. Then we can do something that has a really cute name in GLSL, and it's called swishing. So I just continue and add more x and y's, and I can add an x, another x. This would be a vector of size 3. I could go like yx, yxy, xx, yxx, and yeah. This vector would be longer than a vector of 2 values, but still. I really want to know who came up with the word swishing. Okay, so we have a position, and it's x and y. Let's just try to use that as our value for red. All right. Oh, no. Very quickly going back. Oh. Yeah. So, switching this, going to a vector of size 2, and a position of x. So, we don't see any difference. And why is that? The reason is that we're now using the entire resolution of the screen. Remember, the screen is a lot more than 1 pixels wide. So the x value I'm going to get on the position x is a value going from 0 to like 1,000 and something. And as we remember, the color values has to be a value between 0 and 1. Everything above 1 is just counted as 1. So in this case, let's just try dividing the position by some value. Let's, for instance, try 60, perhaps. Yeah, a little bit more, maybe. 160. And you can see, going back to the image, that we now get the gradient, and it's sort of placed somewhere along in the image. But this is not a really good way to do it. I mean, what we would like to do is to know the resolution of the screen and then use that value in order to get a nice gradient going across the entire screen. And we can do that using something called uniforms. And uniforms is kind of the secret sauce of shaders. It's values that you can pass in from the outside JavaScript environment and into your shader. In this case, I made a resolution uniform, and it contains 2 values, and that's the width and the height of my screen. And since that's a vector, and we can do vector manipulation here, I can just divide this by U resolution instead. And in this case, I get a nice gradient going from several different directions. So, can we do anything more interesting with this? Yes, we can. Introduce more uniforms. Let's introduce one for sort of time. So one way of counting time when you're working with shaders is to count the number of frames you have produced. So here we have one integer that starts at 0, and then it ticks up with 1 every time we render a new frame. So let's try to do something interesting with that. Maybe multiply our x position with it. And since this is an integer, I have to do a conversion from int to float. And in GLSL, this is simply done by saying float and then passing it an integer. All right. Yeah. We see we get sort of the same problem as last time. Since UFrame is very rapidly rising, it's not long before our little effect is faded all the way across the screen. But fortunately, there's stuff we can do about that. Remember sine and cosine? The magic functions you can put any number into, and you get something that's somewhere between 1 and minus 1. Well, they come in useful now. So let's just try to go sine. And I know this will flash a lot if I don't reduce the number of times the sine go from 1 to -1. So I'm just going to divide it by, let's say, 60 again. All right, and then I need final. This one, perhaps. Let's see. Oh, yeah. Thanks. All right, so now we get this small burst of red, and then we have to wait a lot. And that's because we're working with values from 0 to 1. And in this case, we get the value from 1 to -1. And the way you can fix that is to take the absolute value. Then it will go from 1 to 0 to 1 to 0, and so on. All right, let's go there. And it's flashing a bit more. Another nice way to do this is to do the same thing for all the coordinates. And then you can vary between sine and cosine in different periods in order to get a flashing effect that is more random. And as the different waves of sines and cosines overlap, you'll get different patterns. But let's try to finish up very quickly by making the pixel stands. So we can make an interesting uniform by using something called a texture. And a texture is an image that you pass into your shader, and you can access different color values from that texture. Usually the texture is an image with colors, but since we're working with web, we can use WebGL to get frequency information about music playing. And then we can use that frequency information to generate an image that is based on the music that's currently running. So let's just try to finish up with that. Here we have loaded a uniform containing the texture with music. I'm only loading the music as the alpha values, so all the color values are 0, so that's why we're only using W to get something. And let's try to do it on the alpha value, since we haven't done anything with that yet. Yeah, and that sounds reasonable because there's no music playing. We probably should put a little bit more saturation due to this projector being sort of a little low in color.
Hey!
All right, I have one final note. Using... Ooh. Ah!
Where is music?
Instead of using the alpha value, that can be a bit harsh. You can instead use the color values. So in this example, I see now I use the music position as a value to the red and the green colors. And then we get a more somber and easy to watch illustration. If we can jump out for a little more music, we might get something slightly resembling a Northern Lights. All right, thanks for listening.